Hello and welcome to the lecture on optical instruments for General Physics 2. Here we're going to talk a little bit about cameras, microscopes, and telescopes. One of the broad principles that underlies all of these devices is that they very often involve multiple lenses, and we need to think about how multiple lenses act together. And the basic principle is this: if you have multiple lenses, that the image that gets produced by one lens, the first lens in your system, acts as the object for the next lens, and then if you have more than that, you can use the image from the second lens as the object for the third lens, and you proceed with the normal sorts of uh, characterizations that you do with single lens systems. But you have to pay attention to where things are, because in some cases objects that turn into images are real, in other cases they're virtual, and so the relative ordering of everything in the system ends up mattering. So I think the best way to talk about that is to look at an example. This problem reads that a converging lens with the focal length of 12 centimeters is located 30 centimeters to the left of a diverging lens with a focal length of 6 centimeters. A postage stamp is placed 36 centimeters to the left of this converging lens. So where is the final image of the stamp? What is its overall magnification? Is the final image real or virtual, upright or inverted, larger or smaller? Well, I find it helpful, even if I don't have to do it for the problem, to sketch what's going on. So here's my sketch. I have a postage stamp here, 36 centimeters away from a converging lens, and then that is in turn 30 centimeters away from a diverging lens, and the focal lengths of the lenses are given in the problem statement. So for now, we just ignore what happens in the diverging lens and focus on what happens through the converging lens. So let's find the image through that first lens. We've used the thin lens equation before. You can rearrange it to say that the inverse of the image distance is equal to 1 over the focal length minus 1 over the object distance. And if I plug in those known distances of 12 centimeters and 36 centimeters, I forgot my little minus 1 here, you find that the image distance is 18 centimeters. So that means the image will be located 18 centimeters to the right of the converging lens over here in the area between those two lenses. And this is a real image, like we get when we produce an image through a converging lens when the object is further away from the lens than the focal point. So if that's 18 centimeters from lens number 1, it's 12 centimeters away from lens number 2. And that's what I use for my object distance when I do the same calculation for lens 2. So the focal length of lens 2 is negative 6 centimeters. It's a diverging lens. Minus 1 over the 12 centimeter object distance for the lens number 2. And if I solve that out, I get minus 4 centimeters, which means ultimately that the image of the stamp is located here 4 centimeters to the left of the diverging lens, and viewed through this system of lenses. So if your eye was on the right, this is a virtual image because you get a negative image distance for your final result. The second part asks us, what is the overall magnification? And magnification is a ratio of how tall the image is to the object. So you can actually take the magnification through lens number 1, multiply it by the magnification through lens number 2, and you get the overall magnification in this system. Well, the magnification through lens number 1 is the negative of the image distance in lens 1 over the object distance in lens 1. For lens 2, it's the negative of the image distance in lens 2 over the object distance of lens 2, and we know all of those numbers. So that's negative 18 over 36. That fraction is a half. And this one is negative 4, so that's a positive 4 over 12. And that's 1/3, and 1/2 times 1/3 is 1/6. And the final answer is negative in terms of the magnification, which means if the stamp was upright in its original location, when my eye is over here on the right viewing it, it would be flipped upside down relative to that. Is the final image real or virtual? We have addressed that. The final image is virtual, formed by this diverging lens. Diverging lenses only form virtual images. Is it upright or inverted? Well, the minus sign here tells us that ultimately, relative to the original object, the image is inverted, and that fraction is less than 1, so it tells us that the final image is smaller than the original object in that system. So a camera, most cameras that we use today have systems of multiple lenses, but a camera is actually a system where you can have one lens, or in the case of a pinhole camera, which you may have made before in your past to view a solar eclipse or something like that, you can actually argue that you can make a camera with no lens, where the pinhole acts as the lens. But the simplest camera has a single lens, but any camera you're going to buy today is going to have a whole series of lenses generally in any quote-unquote lens attachment, and those are put in there to produce certain characteristics of the final image. But we can model a camera like a system with a single lens, which is much like the eye. But unlike the eye, which we talked about in the previous lecture, you don't change the focus by changing the focal length of that lens. This lens has a fixed focal length. Instead, you change the position of that lens relative to, well, used to be back in my day film, and now it's photo sensors there in the camera where the image is going to be produced. So we'll do a sample problem to illustrate how you would look at a camera problem. A camera is supplied with two interchangeable lenses whose focal lengths are 35 millimeters and 150 millimeters. A woman whose height is 1.8 meters stands 8 meters in front of the camera. So what is the height of her image on the film as produced by each lens? So here we know the two focal lengths and we know the object distance, since this woman is going to remain a stationary 8 meters in front of that camera. And that means we can actually combine our two lens equations that we were using, the magnification equation, which relates the image height and the object height, and the thin lens equation, which relates the object distance, the image distance, and the focal length. And I can actually rearrange my magnification equation to say that the image height is the negative of the ratio to the image distance to the object distance times the object height. And that is going to be equal to, if you solve the thin lens equation for image distance, this equation. So I've just gotten rid of image distance in there, since that's the one thing I don't know in this particular problem. And everything else I do know, and I can plug in for the two scenarios that we're given. So lens number one is 35 millimeters. So that's 1 over 35 millimeters. The woman is 8 meters in front of the camera, so that is 8 times 10 to the third millimeters. So I left everything in here in millimeters, which means in the brackets I'm going to get a quantity that has units of millimeters. I left her height and her distance in units of meters because both those cancel out. And my answer, final answer then, is going to have units of millimeters. It's negative 7.91 millimeters, and that tells me that the image is 7.91 millimeters tall. The negative sign tells me that it's inverted relative to the direction that she's standing. If I do the same calculation for lens number 2, the only thing that changes is now I have 150 millimeter focal length, but that has quite a sizable difference. It produces an image that's nearly 35 millimeters tall. Some of you that are photographers probably know way more about this than I do, but there are several common ways to characterize cameras and camera lenses. There's an F number, which is defined to be the focal length of the particular lens divided by the diameter of the aperture. But more commonly, people actually set the diameter of the aperture, which is more commonly called the f-stop setting. And that is, if you rearrange the top equation, the focal length over that F number. And so you'll get f-stop settings of, say, f over 2, f over 4, f over 8, etc. And what you're doing when you alter the f-stop is you are controlling the diameter that the aperture of your camera opens up to. And that controls how much light is let in, and it also controls the quality of the image. There's also shutter speed, the amount of time that the shutter is open for, and so those are often in small fractions of a second, a thousandth of a second, a 500th of a second, etc. And both of those things can affect the quality of your image. The more wide open the shutter is, the more light is let in, but generally also the more distortion rather you get of the image. Smaller aperture lets in less light, but you get a higher quality image typically. And the shutter speed, same thing. The longer it's open, the more light it lets in, but also you can get worse images that way. Often, you increase shutter speed in low light to let more light in, but if things are moving, that's going to produce a blurry image in your camera. Another topic that becomes important, especially when thinking about the two devices we're going to conclude this lecture with, microscopes and telescopes, is the concept of angular magnification. So I don't know if you've ever tried this, but if you hold a penny out at the length of your arm on some night when there's a full moon out, that penny will actually look larger than the moon. You can cover the entire moon with a penny. In fact, I think it's something about the size of a pea that is needed at arm's length to cover the moon, which surprises most people because to most of us we would say the moon is much larger than that. But the size of how big the image is on the retina determines how large our brain thinks objects are. And the angle is the angular size of the image and that object. And so here's a little diagram to illustrate. There's my cutaway of my eyeball. I'm producing an image on the retina back here in the back of my eye. I'm looking at an object over here, and both of those take up some amount of angle of my vision, and those two angles match one another. So if the angle is small, then that angle, which we're measuring here in radians, is the angular size, and that's approximately equal to the height of the object over the distance to the object. You may recall from your trigonometry studies that when theta is small, the tangent of theta, which would be the opposite over the adjacent, is approximately equal to theta itself. And most of the cases, theta is small, especially when we're looking at things that are far away from us. So an optical instrument magnifies the angular size of the object. Why do we use binoculars? Because we want to make something appear to be larger. Why do we use a telescope or a microscope? Again, we want to make something appear to be larger. So when we're looking at the magnification, we're looking at the ratio of how big that angular size of the final image is, how big we've made the thing appear to be, over the angular size of the original object. And I believe we have, a different picture for that. So here is an eye looking at an object at some angle theta. But if we put some sort of lens in the system, like a magnifying glass, we very often make that object look hopefully larger, and that's going to be a different angle, which we're calling theta prime on this particular diagram. So it makes that object appear to be larger than it is. Even though it's further away, the overall effect still is a magnification there. And you can find this angular magnification in terms of things that are known in the system. So that magnification is, again, the ratio of those two angles. But if the angles are small, then that apparent angle is the height of the object over the distance to the object. That little triangle there, the distance to the object being the distance from the magnifying lens out to the object. And theta, the angle when we don't have the lens in front of our eye, is approximately equal to the height of the object over n, the near point, that closest distance we can bring an object to our eye and still clearly focus on it. So those heights of the objects cancel out, and the magnification can also be calculated, or at least approximated, by the near point distance over the distance to the object. So let's look at a sample problem that illustrates the use of angular magnification. If you are a jeweler, you might spend some amount of your time looking through lenses at things that are or are not precious and trying to decide just how precious they are. This problem reads: a jeweler whose near point is 40 centimeters from his eye and whose far point is at infinity is using a small magnifying glass to examine a diamond. The lens of the magnifying glass has a focal length of 5 centimeters, and the image of the gem is 185 centimeters from the lens. Notice it's negative because that's a virtual image that you're forming when you're holding an object this close to the lens. The image distance, I guess I just said that. The image distance is negative because the image is virtual. We want to find the angular magnification of the magnifying glass. Where should the image be located so the jeweler's eye is fully relaxed and has the least strain? And what is the angular magnification under this condition? So, here's a sketch of the setup. We have the jeweler's eye here. We have a lens that is in position. You're looking at some diamond. And that diamond image appears to be 185 centimeters away. So it's making it look larger, even though it's also making it look further away as the jeweler looks at this. So let's figure out what the object distance is. How far is this diamond actually from this lens? Well, we can use the thin lens equation and say the object distance is 1 over the focal length minus 1 over the image distance, and invert that all. So I know my focal length of my lens is 5 centimeters. My image distance is negative 185 centimeters. And I work out an object distance of 4.87 centimeters. So I'm holding this thing pretty close to the focal length of this particular lens. What's the magnification, M? Well, the magnification is the ratio of that near point distance over the object distance. So with just his eye, the jeweler could only hold the diamond 40 centimeters away and be able to see it. But the object distance relative to that lens is 4.8 centimeters, which means we're getting a magnification of 8.22. This lens in this arrangement is making the diamond appear about 8 times as large as it would be without that lens. Where should the image be located so the jeweler's eye is fully relaxed and has the least strain? Well, your eye strains the least when you're looking at light from far away, and far away is code for assuming infinity in your calculations. Now, we can get into an argument, I suppose, as to whether or not one can actually see light from infinity. Of course, if light originated an infinitely far distance away, it would take an infinite amount of time to get to us, but let's not wax philosophical on this. If it makes you feel uncomfortable to use infinity, just put in a really big number there. So the object distance is 1 over the focal length minus 1 over the image distance, and if I plug in infinity, I'm going to find an object distance of 5 centimeters. If I'm going to get this image to be way, way far away, I'm going to put this diamond out at the focal length of the lens. Again, when it's at the actual focal length, you're not really going to see it, so perhaps a better answer is 4.99 centimeters or something to that effect. But if we use the theoretical 5 centimeters and calculate the new magnification is actually a little bit less than it was before. It's 8, but the jeweler is experiencing a slightly less eye strain in this configuration. All right, let's think a little bit about microscopes and telescopes. Microscopes are objects that have 2 images, and typically you're looking at something that's very small down here at the bottom of the diagram, and you're trying to make it appear larger. And you can accomplish making it much larger with 2 lenses than you can with a single lens, and we'll show that subsequently here. So I have an object to be viewed, and I get that pretty close to the focal length of my first lens, which is my objective lens, the lens that's near the amoeba or whatever it is that I want to look at in my microscope. Well, you can use your ray tracing ideas from lenses to show that, okay, then I'm going to form an image. And as long as that object is outside the focal length of the objective lens, I get a real image formed here at some position. But if I adjust an eyepiece, a second converging lens, so that the eyepiece is, the focal length of the eyepiece is the same place as the position of this image formed by the objective lens, I'm going to actually then form an image out here at infinity, which is the best for eye strain. I can look at this with a fully relaxed eye and see the image. Again, of course, you can't do it really at infinity, but you're trying to make that image look as far away as possible by getting this position as close to the focal length of the eyepiece as possible. And when you want to worry about how big you're making something look, the angular magnification of the microscope is multiplying the magnification of both of those lenses. So you multiply the magnification of the objective lens and the magnification of the eyepiece lens. The magnification of the objective lens is the ratio of the image distance to the distance of the object in the objective lens. And the magnification of the eyepiece lens we've shown is approximately equal to the near point of whoever is viewing this system through the eyepiece over the object distance in the eyepiece lens. And since we want to get these things as close to the focal lengths as possible, the distance from the object to the objective lens is approximately equal to the focal length of the objective lens. Similarly, the distance from the object to the eyepiece lens is approximately equal to the focal length of the eyepiece. Again, we're treating the image through the first lens as the object in the second. But that means you can write the total magnification as the image distance times the near point distance of the observer divided by the product of the focal lengths of both lenses. So let's use that to solve a sample problem. This problem reads, the focal length of the objective of a compound microscope is 0.4 centimeters, while that of the eyepiece is 3 centimeters. The two lenses are separated by a distance of 20 centimeters, and a person with a near point distance of 25 centimeters is using the microscope. So what is the angular magnification of the microscope, and how does this compare with the biggest magnification you could get if you only used a magnifying glass, i.e. just use the eyepiece alone without the objective lens? All right, so to find the angular magnification of the microscope, so I've sketched the picture of the microscope. I have my eyepiece lens up here. It has a focal length of 3 centimeters. The objective lens down here has a focal length of 0.4 centimeters, and they're 20 centimeters apart. So I'm looking at something down here below the objective lens. And what we would like is the image from the objective lens. So whatever image gets formed by this lens in this middle region, we'd like it to be at the focal length of the eyepiece. Therefore, we know that the image distance, the distance from the objective lens to where that image forms, would be 17 centimeters, because it would be the 17 centimeters and then the 3 centimeters remaining is the focal length of this eyepiece lens. Once we've realized that the image distance is 17 centimeters, we can go ahead and calculate the magnification. The near point of the observer is 25 centimeters. The image distance is 17 centimeters. The focal length of the objective lens is 3 centimeters. The focal length of the eyepiece lens is 0.4 centimeters, and that's a magnification of 354. So this microscope is making the object look 354 times larger than it would if you did not have the microscope. If you just use the eyepiece, it actually cuts down the performance pretty dramatically, because now the object distance is 20.4 centimeters. So from this lens, you'd be the 20 centimeters here, plus assuming the object was at the focal length of the objective lens, the 0.4 centimeters. The near point distance is still 25 centimeters, and 25 divided by that 20.4 is a magnification of only 1.22. Even if you took that object and pulled it near to the eyepiece lens, the best you're going to get is a distance to the object that is, like just outside of that 3 centimeter focal point, so you're only going to get a magnification of around 8 under the best case scenario with a single lens. Another important two-lens system, but used fundamentally differently, since you're not trying to make tiny near things look large, you're trying to make far distant things look close, and in the process look larger to you. You have a telescope. So a telescope, again, has an eyepiece lens. Again, our goal is a relaxed eye viewing through the eyepiece lens. So we want to look at an image formed at or nearly at infinity. That means we want the image formed by the objective lens to sit here near the focal length of the eyepiece. And we're looking at something that is very, very far away, which is what these broken lines are intending to illustrate here. So how are a microscope and a telescope different? Well, again, they're used to look at different things, but the chief difference is in the focal length of the objective lens. In a microscope, you want the focal length of the objective lens to be very, very short, so you can bring the object as close to that lens as possible. In a telescope, you want that focal length of the objective lens to be very large, so that you can, again, form the image of looking at something very far away, for all intents and purposes infinitely far away, and form its image at the focal length of both lenses. So if you look at the diagram, you can figure out what the angular magnification of the image formed by the telescope is. One angle here deals with the angle formed by the objective lens. So here's theta. I have my focal length of the objective lens, and I have the height of the image formed by that objective lens. The tangent of that angle is that ratio. but that's approximately equal to theta since we have a large distance and therefore a very small angle we're dealing with. Over here in the eyepiece, theta prime, a different angle, is the ratio of the image height to the focal length of the eyepiece. But again, that is theta prime approximately with small angles. The total magnification then is the ratio of those two angles, but that's just the ratio of the focal length of the objective lens to the focal length of the eyepiece lens. Again, this is an approximation, but it's a pretty good approximation when the angles are small. So this sample problem reads that the telescope shown has the following specifications. The focal length of the objective lens is 985 millimeters, and the focal length of the eyepiece is 5 millimeters. From these data, can we find the angular magnification of the telescope and the approximate length of the telescope? Well, yes, we can, and actually this is hopefully fairly straightforward to do. The angular magnification of the telescope is the ratio of those angles, but it's also the ratio of the focal lengths. And we're given the focal length of the objective lens, 985 millimeters. We're given the focal length of the eyepiece lens, 5 millimeters. And that ratio gives us a magnification of 197. We're going to make something look or take up 197 times the angle in our field of vision as we would if we were not using this telescope. Because in a telescope we want to arrange the two lenses so that their focal points lie basically at the same location, then the approximate length of the telescope is just going to be the sum of those two. So I got 985 millimeters to the focal length of my objective lens, 5 millimeters for the focal length of my eyepiece lens, which means the needed length of the telescope is the sum of those two, or 990 millimeters. Finally, I just wanted to make brief mention of problems with lensing and lensing effects. I don't know if you've ever seen this. I myself wear glasses at times, and out at the edge of the glasses, if the glasses are large enough, I get some weird color shifting going on. And that's because no matter what lens you make, you have to sort of decide what properties you want that lens to have and be willing to trade certain features for other features. If you grind a lens so that its two surfaces are radii of spheres, so you have this spherical, you could imagine drawing a giant circle, and this is just cut out of one piece of it. The rays that come through don't actually all meet at the same point. They don't meet at the single focal point on the other place. In this particular picture, the rays that are further from that center of the lens are actually bent more. And so you get these rays that don't all quite cross in the same location. And that's sometimes called the circle of least confusion, the place where the rays are closest to each other and closest to the optical axis. But one way you can cut down on those problems is you make your aperture of your camera or telescope or whatever smaller. And so if you cut off those outside rays of light, you are going to cut off the ones that are the least likely, not the least likely, the least hitting the location that you would like there at the focal point of the lens. Of course, that's a trade-off because by cutting off those outer parts of the lens, you're cutting off the amount of light that you let through the system, and so your image is going to be dimmer as a result. There's also chromatic aberration. So through the same lens, sunlight, which is comprised of all the colors of light, has different wavelengths of light within it, and the amount that light is bent is actually dependent on the wavelength of the light. So violet light is bent more than red light. And so violet light's going to go through one focal point and red light's going to go through a different focal point. One way you can fix that is you can throw in a diverging lens in that system, and that diverging lens is going to bend light the other way. And so here again, when violet bends more, you can work those two lenses together so that the red and the violet light actually come together at the same location. But again, you're sacrificing something because by bending light out, you're not getting it to focus as closely to the lens as you were before. So that's all we're going to look at in this particular lecture on optical instruments. As always, if you have any questions about the lecture, I'd appreciate hearing about them. Also, if you've spotted any errors in any of the sample problems we solved, I appreciate that feedback too. Thank you.